Good morning, everyone. In this session, we are going to see what is Boolean algebra and how we are going to represent this Boolean algebra and everything. So, this is some of the theory which is present over here related to Boolean algebra. And let's get on to the Boolean algebra, like what functions we are going to implement in Boolean algebra. Like basically, we are going to use AND operation, OR operation, and NOT operation. And operation not operation is represented using these kind of symbols. You can see this is one symbol and this is one more symbol, or apostrophe, single apostrophe we are going to use for not operation. Coming to and operation, we are going to use dot or a cap. A cap is going to be represented a and operation. Coming to or operation, we are going to represent a plus symbol or a inverted v value where we are going to use for or operation. So for example, if I am having two variables a and b, how we am going to represent a not operation, and operation, and or operation, we'll see here now. Now if you see here, a and b is equal to true. Like if a is equal to b, means and operation performs only a true value when both a is high or a is true and b is true. Then only my output is going to be true, or else remaining all cases my output is going to be false. Means for example, if I am having, if true is represented with 1 and false is represented with 0. For example, if I am having 0 and 0 0 combination, 0 1 1 0 1 1 combination, so my AND operation output will be 0 0 0 and 1. Means when both are high, then only I am going to be a high output. For remaining all cases, my output is going to be a false. So this is what the AND operation. Now coming to OR operation. Coming to OR operation, the OR operation can also be represented like for A, B and OR operation. OR operation means 0 1 1 0 0 0 1 1 0 1 1. Means if any one of the input is high, the output is going to be high. Means for 0 0 combination, output will be 0. For 0 1, one input is high, so my output is going to be high. Here for 1 0, one input is high, so output is high. For 1 1, the output is always high. So this is what the OR operation. Now when coming to NOT operation, only single input will be there and NOT operation output will be. If I am having 0 as my input, output will be 1. If A is 1, then output is going to be 1. So I can call this particular gate as complement gate also. So this is what the operation of basic AND function, OR function and NOT function. We'll see how the representation goes with the expressions. Now generally Boolean expressions, we are going to have, we are going to represent them using some truth tables. Now AND operation, you can see here, for true true it is true, for true false the value is false, for false true false, false false false. So this is what the operation is. Generally the truth table which I represented over there is the functionality for OR gate, NOT gate and AND gate. So the same tables which are represented here. There are some of the postulates or functionalities of those functions. For example, there is a closure property, means a set S is closed with respect to binary operator if for every pair of elements of S, the binary operator specifies a rule for obtaining a unique element of S. Associative law, second one. Associative law states that, you can see clearly that x dot y dot of z is equal to x dot of y dot z. So this is associative law. Commutative law states that x dot y is equal to y dot x for all values of x. Coming to identity law. Identity law. Now you can see identity law stating that e dot x is equal to x dot e is equal to x. Means the same value I am going to get as output. Means if I am giving x as input, output is also an x. So this kind of thing we are going to call it as identity law. Inverse law. Inverse law is a plus of minus a is equal to 0. Means when I am doing addition of two different things, I am getting a 0 value. Now you can see in the set of integers I, the operator plus with e is equal to 0, and the inverse of an element a is always minus a. So a plus of minus a will definitely give it as 0 here. Distributive law. X dot of y dot z is equal to x dot y dot of x dot z. So this is what different types of laws which are present with respect to the operators which we are using in between the variables. Now if you see here, we are having two binary operators, plus and dot. You can see clearly with respect to operator. Now operators are plus and dot here. Now x plus 0 is equal to 0 plus x is equal to x always. And 1 dot x is equal to x dot 1 is equal to x. Now x plus y is equal to y plus x. X dot y is equal to y dot x. So these are some of the properties with respect to the operators. Let's get on to the next thing. Operator with respect distributive over dot over plus means x dot of y plus z is equal to x dot y plus x dot z. Plus over dot is x plus of y dot z is equal to x plus y dot of x plus z. So these are the properties of distribution. Next, fifth property is related to same variable we have utilized, that is x with x bar means x plus x bar will give me always 1, whereas dot operator will always give me 0, and there exists at least two elements of x, that is y belongs to b such that x not equal to y. Let us see AND law. Using Boolean laws, how we are going to represent those different values, we'll see here. Now you can see clearly that a dot 0 is always 0, a dot 1 is a dot a is a dot a bar is always 0. So this is related to AND operation. Coming to OR operation, you can observe clearly a plus 0 means if I am adding variable with 0, my variable is going to appear as output. A plus 1 is also a plus a is a, a plus a bar is always 1. For example, if I am taking a value to be 0, so what happens? The first condition, 0 plus 0 is equal to 0 only, so ai is getting different. Next, 0 plus 1 is equal to 0, no, 0 plus 1 is equal to 1. So this is wrong beta, this will be 1 value as output. This is 1 at the output. A plus 1 gives me 1 output, so this is 1. Next, 0 plus 0 gives me 0. Next, a plus a bar is always 1. So this is wrongly printed, this is 1 beta as output. Okay, let's get on to the next law. The next law, we'll see the double negation means if I am having two times of representation of something, means here it is given b bar whole bar, that is a bar whole bar. If I am taking a value as 0, 0 bar whole bar, 0 bar is 1, 1 whole bar is 0. So the same element is getting as output. Commutative law, a plus b is equal to b plus a dot b is equal to b dot a. The next law, we'll get on to the next law. Next is associative law. Next is associative law. You can see a plus of b plus c is equal to a plus b plus c. Or else if I am using dot product, it will be a dot of b dot c is equal to a dot b of dot c. Coming to distributive law, a plus of b plus c is equal to ab plus ac. Or else if I am using plus operator, a plus of b dot c is equal to a plus b dot of a plus c. So this is distributive law. Next, absorption law. Next, absorption law. We'll open it. Now, this is in absorption law states that a plus of a dot b is equal to a dot of a plus b is equal to a, and a plus of a dash b is equal to a plus b. A dot of a dash plus b is a dot b. Next is De Morgan's law. Very important law this is. You can clearly observe a dot b is equal to a dash b plus a b dash. Now we can prove this law also. If I am having inputs as 0 0 0 1 1 0. Now I will take a dash and b dash separately, means 1 1 0. You can see 0 0 1 1 1 0. Next for 0 1 0 is 1 0 1. Now I want dot product between or between these two elements. First I will take, this is for dot product. Dot product is 0 0 0. So whole dash will become 1 1 1. For or, this is going to be 1 1 1. Now if you observe clearly, a dot b whole bar is equal to a bar plus b bar. These two columns are equal. So kindly remember this law. It's very important law for at the examination point of view. Now De Morgan's second law. If I am having a plus b whole bar, then it will be, the output will be a bar dot b bar. You can see clearly for 0 0 0 1 1 0 1 1 combinations, I have taken a bar and b bar. Then I have done a plus b whole bar, and a bar dot b bar. If I am performing, I am getting two columns similar. So this is what the De Morgan's law state. A plus b whole bar is equal to a bar dot b bar. A dot b whole bar is equal to a bar plus b bar. Next, duality principle means if I am changing AND operation to OR operation, or OR operation to AND operation, means plus is converted to dot, or dot is converted to plus, and replacing with 0 to 0 with 1 and 1 with 0. If I am getting the same operation, such kind of operation we call it as principle of duality. If it is if it is satisfying these four conditions, such equation, such Boolean algebraic expression, we are going to call it as duality expression. Generally those kind of things will exist in a fewer number. Now you can see here x plus x is equal to x. Now place I am replacing replace with the dot, x dot x is equal to x1. So these are the some of the examples which are present for principle of duality. Now this is also one of the example. Like we are proving all the properties, x plus of y plus z is equal to x plus y plus z. That is how we are representing this representation. Now if for x, y, z, the three input variables can go values from 0 0 0 to 1 1 1. If you observe all these things, the values at the output level, you can see x plus of y plus z is having the same values with x plus y plus of z. So this is how we prove the given expressions using truth tables. If you observe this particular thing, uh, now see x of x plus y is equal to x. Now I have taken x and y, 0 0 0 1 1 0 1 0 1 1. So for x plus y, you can observe clearly when I am performing OR operation between x plus y, 0 1 1 1 will be my output. Now x of x plus y means I need to perform AND operation between x and x plus y. Now you can see here 0 0 1 1. Now when I am performing 0 0 1 1, these values are exactly equal to x. So this is how we prove the given expression. Let's see the other one. Now x plus 0 is always x. Next, x dot 1 will be always x. So this is one proof. X plus x bar is always 1. I told you that there was a wrongly representation. X plus x bar is 1. Now x dot x bar will be 0 in this case. X plus y is equal to y plus x always. This will be always true. And x dot y is equal to y dot x. So these are the few of the expressions which we proved using uh, truth tables. All these functions we call it as Boolean expressions. So these are the few of the examples which we can represent using truth tables. Okay, we are going to end the session here. We'll continue in the next topic. Thank you, one and all.